Okay, since I'm the last speaker, let me so this thanks to organizer. So thank you. Thank you very much. And yeah, it's my great pleasure to come back to IMSA and give a talk. So yeah, thank you very much for the invitation. So today I'm gonna talk about the Motivic aspect of logarithmic transformation. So Motivic aspect of log transformation. So this is based on joint work with and Ernesto Lupercio and Laurent Meersseman. Okay, let me start. So since this is a bilateral geometry conference, let me start from very classical theorem. I think everyone knows actually. So when S is a smooth projective surface, and if Q is equal to 0 and H 0 as K is 0, then it proves that this proves that it's rational. So today I walk over C for the time. So so he proved this very classical result. And then, people ask if there is a surface with, so of course this implies that this geometric genus is 0. So after that, people ask if there is a, surface with PG equal Q equal 0 sense. And there are lots of, actually, indeed, Max Neder asked that if surface has PG and Q equals 0, then if this is rational, and of course we know that this is not the case. So the first example, the first counter example was constructed by Enrique in 1896, and later Topadelli and Godot constructed, surfaces with PG equal Q equal 0, which is not rational. Okay, so and as Ludmil already showed us, when S is a surface with PG equal Q equal 0, then its bounded derived category has a non-trivial semi-orthogonal decomposition. This has non-trivial semi-orthogonal decomposition, and especially when S is a rational surface, then its bounded derived category has for exceptional collection so which means that we can we can decompose this derived category of S into derived category of Carpio points.
What's the full exceptional collection of Enrique's surface?
In a rational surface case, when S is rational.
Oh, is rational.
Yes.
Sorry, I thought it's irrational.
Sorry, it's rational.
Okay, yeah.
Yeah, thank you. You're right. So when S is rational, actually this is basically comes from Borlow's formula, anyway, you see that derived category of S always has free-exceptional collection. Okay, so then, I mean, from this historical point of view, we can ask if we can detect rationality from, derived category point of view, as, I mean, we see many similarity during this conference. So, okay, then what happened to non-rational surface? So let's discuss this Godot surface case. So let us consider a surface looks like zero in P4, and I have G mod 5 action, certain G mod 5 action, and if I take quotient of this surface, then I mean Godot actually proved that this is surface with PG equal Q equals 0. And so then it's natural question that if this has free exceptional collection or not. And there's a theorem by Bosman, Bosman, and Sosna to prove that the bounded derived category of current shift on this surface has exceptional collection of length 11, but it's not full. So there must be some orthogonal complement part. So, and actually this category has very interesting property. First, this cannot be detected by Hertz theory, which means that its Hochschild homology is zero. And but it can be detected using this Grothendieck group. So its Grothendieck group of this category is exactly G quotient. So this is called quasi-phantom category because it is believed that category with this property, which I mean couldn't be detected by Hertz theory, will not exist. But I mean this gives the first counterexample of such conjecture. So this is called quasi-phantom category. And later, Ludmil and this group, named Bosman, Sosna, and Katzarkov, proved that actually there is phantom category. So there is a theorem by Bosman, Sosna, and Mill proved that when S is so-called determinantal Barlow surface, then its bounded derived category has again exceptional collection of length 11, and it's also a complement. And this category now has Hochschild homology zero, and Grothendieck group is also zero. So it's kind of category which can't be detected using this additive invariant. Okay, so then so this is somewhat expected pattern. So if you have a rational surface, then you have free exceptional collection, and if S is not rational, then this kind of category is somewhat obstruction to be this surface to be rational. But unfortunately, we actually do not know how to understand this category systematically. So this is phantom category. It's some interesting phenomena, and many people believe that this is obstruction for rationality. But I mean, still we don't know how to study this phantom category systematically. So let's go to a little different surfaces. So these are surfaces of general type. So let me consider some Dolga-shape, so-called Dolga-shape surface. So let S be, blow up of 9 points at P2. So of course these 9 points are intersection of two pencil of two quadric, two conic, two cubics. So I consider pencil of two smooth cubic, and then I have this blower, and then this become elliptic surface as we know. So this has elliptic vibration to P1 induced by this pencil. Then I do so-called logarithmic transformation. I have this log transformation to obtain surface, a new surface, which is so-called Dolga-shape surface. This is surface with PG equal Q equal 0. So I obtain this new surface, which is not rational, and one can prove that this is not rational because the Kodaira dimension is 1 for this case. So it is quite interesting what happened to this, this non-rational surface. Anyway, it has non-trivial semi-orthogonal decomposition because this is surface with PG equal Q equal 0. But so it is, somewhat expected or conjecture is this bounded category of this Dolga-shape surface has exceptional collection of length 12, and it's also on a complement path, and this becomes phantom. So then this zero and cross anti. So it is expected that this also on a complement has this property, and indeed there are some example with this property. So there is a theorem by Kyoung-Seog Lee and Yong-Ah Cho. So there is a theorem by Yong-Ah Cho and Kyoung-Seog Lee, and also Ilya Katzarkov and Ludmil, saying that there exists Dolga-shape surface with expected semi-orthogonal.
Sorry, is it true, correct me if I'm wrong, that S itself also has quantum categories? No?
S is here.
Yes.
No, I mean good. That's good point actually. Yeah, that's actually a good point. Because for this case we don't know. But there is very famous, an interesting recent.
There was the recent result on some 9 points on P2 and.
Actually, indeed, this is 10 points. But anyway, So 9 points we don't know, but 10 points there are recent theorem by Kra.
Yeah. Sorry.
Kra saying that if I have blow up of 10 general points of this P2, then there exists semi-orthogonal decomposition of this surface with 13 exceptional collection of line bundle, and this is phantom. So indeed, semi-orthogonal decomposition is not unique, as Ludmil already mentioned. We can find. What I mean is that we can construct another semi-orthogonal decomposition, which is full, and there's no phantom. If we construct nice semi-orthogonal decomposition, then it's full. But there are certain ways to construct semi-orthogonal decomposition such that this is not. So indeed, this SOD is not unique. Yeah, that's very good point. And in this case, as you see, this is, I mean, for 9 point, as far as I know, there's no example. No.
I mean, there is some numerical abstraction which tells you that in some cases that's impossible, but these two are not among them. So there's this channel, whatever his name is.
For any surface, there's numerical.
No, I don't think the request field fits in that.
No. For any surface, we can't construct exceptional collection of maximal length. So it's impossible. Right?
I mean, just because, I mean, request, there's also this piece there which looks like let's say, a little bit like the construction of Ernesto curve. Yeah, it has to be there.
Yeah. I mean,
but this doesn't mean that there is no other semi-orthogonal composition which includes the exceptional object plus this category plus some atoms.
yeah.
Plus some atoms.
Right. So anyway, yeah. Thank you. And anyway, it's a good point that this is not unique.
I mean, so the reason of, I mean, historically, the reasons that the theory of atoms was developed was because phantoms appeared and became clear that it's not going to work. Then actually, all these results can take some additional, I think actually probably they are wrong, but some additional structures needs to be considered. But what is an interesting question, Armand, here is that is it true that we could have, let's say, four-dimensional Fano varieties which have semi-orthogonal decompositions, and all the atoms involved there, for all categories there involved in the semi-orthogonal decompositions look like category of a curved surface, and still, I mean, this is not rational. So most likely there is some invariant coming from logical modular forms, so it's part of a paper that Laurent didn't talk about, where the elliptic genus actually measures this kind of thing.
Yeah. Thank you. So anyway, so yeah.
In other words, there is a paper which kind of appeared in some of these Stolberg, Kyoung-Seog Lee, I forgot who else, where they show that there's a rational four-dimensional cubic, which is not some big group.
Oh yeah, but equivalent Kuznetsov doesn't work.
And so, I mean, I always thought that this is stupid, but not anymore.
So anyway, we have lots of examples of phantom category now, but unfortunately, I mean, as far as again, let me say that it's still not, it's quite mysterious how to understand this piece, which it's not, I mean, it isn't so clear. So anyway, let me suggest, I mean, kind of, way to understand, I mean, not trying to attack this problem. So, well, I mean, so actually there's kind of parallel theory whenever, I mean, as we already saw many times in this conference, there's kind of parallel story when to this derived category and this theory of motive. So for example, there's conjecture by Orloff says that, I mean, derived category and motive is very closely related. So, well, I mean, to be precise, let me say that, this derived, so he conjectures something like this. So let X and Y be two smooth projective variety. And then if, first conjecture is if derived category of X is equivalent to derived category of Y, then its child motif, right? Actually, rational child motif is same as, you know, this child motif y, rational child motif, child motifs, rational. And if derived category of x is embedded into derived category of y, then the rational child motif of x times certain Lefsetz motif is direct summand of some kind of part is child motif. So anyway, his conjecture has several evidence. Of course, some people believe it, some people don't. So anyway, it should be it's quite fair to say that this theory of motif is closely related to this this theory of derived category. And I want to speak more simpler version of motif, which is called Grothendieck ring of variety. So if this Grothendieck ring of variety is nothing but free abelian group generated by isomorphism class of algebraic varieties. Algebraic variety modulo certain relation where this x is same as xg plus g, where g is closed algebraic subvariety. Then this is, you can consider it as kind of Bailey version of motif, since there is a map from this Grothendieck ring of variety to the Grothendieck ring of child motifs. So, well, from this sense, this can be somewhat stronger invariant from this sense, and also one can, but this is a little more subtle than derived category in a sense, because there is as you already saw in other talks, that there are certain examples that exist, x and y, which are Calabi-Yau variety, such that its derived category is same as this derived category, but it's the difference between this class is non-zero in Grothendieck ring of varieties. So in this sense, this invariant is a little more sensitive than derived category itself. And there are various perspectives. And indeed, Kuznetsov and Schindler conjecture that if derived category, if Schindler conjecture that if its derived category is equivalent, then the difference is zero divisor. It's a zero divisor Grothendieck ring of varieties. So from this sense, so this invariant is a little more stronger.
Is it computed in some Fourier-Mukai partner for surfaces?
Yeah, as you saw, this case-free surface case, there are two cases whose derived category are different. The difference is not zero.
No.
There are some examples.
There was a.
No, I'm talking about this Sasha's and Schindler's conjecture.
It comes from this word Lupercio.
Yeah. The first zero divisor. Actually.
So let me historically, there was an approach first by Kulikov, which was saying that Renaissance split as two whole structures of waves too. Then it can prove knowledge that eventually with four dimensions too. But that's wrong. So yeah, the opposite surfaces. That's true. And so then Schindler and Dawkins came this never zero divisor and that it to approach the four-dimensional knowledge type the four-dimensional. But then in a very smart way using similar patterns to get the surface impulse actually show this zero divisor and this is where this conjecture came from.
Yeah. So yeah, indeed. So yeah, to be honest, I slightly, miswrite their conjecture. So as Ludmil mentioned, it was big conjecture that if this class of affine line is a zero divisor. So if this class of affine line is zero divisor, and most of the examples so far to construct zero divisor, something times this makes zero is you consider two derived equivalent variety, and then you measure which are not birational to each other. Then you take the difference and you cook up some it's an affine line and then times it, and it becomes there's this kind of tendency to create examples. Thank you. So anyway, so then from all this perspective, what I want to say. So I want to say something about phantom category, but as I told you, for all these examples, this this, for example, all the example I told you, this charm motif of this surface is actually same as charm motif of rational surface. So so what I mean is that for rational charm motif, this phantom category is kind of cannot be seen. So then we still have hope because this is then we still have hope because this is morphism, but there can be kernel. So we can still hope that this guy can be seen from this derived category of this motif. And actually there is a variant of this Grothendieck variety. So I consider this. So if E is an algebraic variety, and then I consider Grothendieck ring of varieties over base. So this means I consider algebraic variety over certain base, and this relation is the same, but the product structure is x times y is just defined by x times the fiber product. And then the first theorem I want to mention. Myself, and Lupercio, Meersseman says that if S and I do this log transformation, and suppose that if both of them are algebraic, then over a certain curve, and I do log, what I mean is that I consider an elliptic surface over a curve, and I do log transformation, so to obtain another surface, and then these are, as you see, this can be quite different as you see Dolgachev's examples, but see that, but if both of them are algebraic, then the difference between these two is a zero divisor over Grothendieck ring of varieties over C. So from this sense, this can be kind of a way to understand how this phantom category should look like. As I told you, this Dolgachev surface case, it is believed that this category has phantom category in it, and we think this is one way to approach for how to measure this phantom category.
So it's not zero.
Yeah, it's not zero. Yeah. It's not zero in general. Sorry, I should say that it's not zero in general, as Dolgashov example say. And but it's still, this is zero divided. So this is not zero, but very close to zero. Okay, and then
And what is the, I mean, how do they call it? The guy that makes it zero?
actually the proof is very easy. So let me thank you very much. So let me just so in this case, I can the point here is I can always find very nice. I mean what I mean is that I can consider a very nice covering of this ramified covering of this curve, such that whose fiber product of the both these fiber products become smooth and birational to each other. And this is smooth and birational to each other. So this is related by blow up, blow down. And then we can check that actually this becomes zero. The difference is zero. Thank you. The idea is very simple indeed. So and then but in general, I mean log transformation, I mean it's somewhat different direction from now on. So but in general, log transformation is very analytic operation. Since lack of time, I will not say what is log transformation. But log transformation can be quite wide operation. So let me say a remark that a log transformation can log transformation does not respect algebraic category. Does not preserve algebraic category. So which means that if I have a rational surface, algebraic surface, and if I do log transformation, but there are cases that this is non-algebraic. So there are example of rational surfaces such that this is algebraic, but this becomes non-algebraic. So this is quite wide operation, you see, and basically analytic. So we become wonder what can we say for this non-algebraic. Can we say something like this for this non-algebraic case too? So in order to do that, so by motivating all this, we want to find some analogy of this theorem. So then, we want to, consider something, some kind of Grothendieck ring of variety, which generalize this algebraic category. So I consider this, I need so-called O-minimal structure. So let me give a very brief explanation what is O-minimal structure. So a subset, a collection of subsets. For each a collection of subsets Sn, subsets of a collection Sn of subsets of Rn is called a structure if it has several conditions, but first it's kind of it form a Boolean algebra. It form a Boolean algebra, and there are several conditions. And the most important thing is, so let me not write down all the definition, but it's first need to be Boolean algebra, which means it's closed under taking finite intersection and finite union and complement. And the fourth condition is if I consider the linear projection from Rn plus 1 to Rn, and if I have a subset here, and if A is, so please note that Sn is collection of subsets of Rn. So if A is n plus 1, then its projection should leave. So it's kind of, preserved on the projection. And it is called O minima. A structure is called O minima. And a structure is O minima. Again, still there are some condition which I don't want to write down. But important condition is S1. So the one-dimensional, collection of one-dimensional subset of, is just consists of a finite union of points and interval. So then this is called an O minima structure. And so then so for each, so let S be an O minima structure. Minima structure. And if I have a set in Sn, then I will say this is A is definable. And if I have two function from a subset of Rn and subset Rn, and F is definable if its graph is definable, then I will say this is an O minima, so definable function. And then I can, so since I have set and function, I can do geometry. So I consider, so there are so-called O minima geometry. So let me give one example and go further. So actually there are, the basic example is so Sn is called a semi-algebraic set. So which means that for each n, I consider finite number of polynomials, real polynomials, such that this set is defined by zero set and some inequality where fi and gj are real polynomials. Then this is called the semi-algebraic set. This and this complement of this guy, and this is called semi-algebraic set. And there's very famous theorem of Tarski and Seidenberg says that this is O minima structure. Algebraic sets are O minima structure. And the other example is so-called restricted analytic function. So this is so-called, let me not say this, but restricted analytic functions on this Rn, and this is theorem of Gabrielov. Well, a little confused. Okay, anyway, yeah, this is only structure. Okay, and why I'm saying all this? So because I consider then complex manifold, then there's a famous theorem by Kodaira and Stashenko prove that for any any compact complex manifold is definable over this O minimal structure and its expansion. So this is always definable. Then I have a perfect category to work with. So to describe the theorem I mentioned, because any compact complex manifold is now definable. And why I'm saying all this, because then I consider this Grothendieck ring of definable space. So this is by definition the free abelian group generated by compactifiable complex analytic space, compactifiable and definably compactifiable compact analytic space modulo certain relation. So this relation is exactly the same. So I have this is same as xg plus g, where g is definable closed analytic subvariety of my x. So x is definable definably compactifiable complex analytic space, and I consider it a closed analytic definable subspace. Then I can define this Grothendieck ring of definable analytic space. So why this is why I'm doing all this stuff. So let me just mention a few remarks. So I introduced this space because one can prove that I see with Ludmil and Ernesto and Laurent says that I can so sorry before going down. So this the lens mixed out structure says that if I consider this Grothendieck ring of variety, and every variety has a canonical mixed out structure, and then I consider it Hot polynomial, which says variety to this HC PQ x u to the p v to the q, and this goes to here, and actually this is a ring homomorphism. And we know this from the lens mixed out structure theorem. And what I want to say is, for compact complex manifold, we can still define this Dolbeault cohomology. So I want to define some similar theorem similar like this. But if I consider this, if I omit this definable structure, then this is not well-defined ring homomorphism. So I need this definable structure to guarantee that this same map gives a ring well-defined ring homomorphism. So here, this the same map x goes to HCPQ x u to the p v to the q, and this is a well-defined ring homomorphism, and this is also run by Ludmil and myself and Ernesto, and Laurent says that there is a well-defined ring homomorphism from here to here, and without definable structure, this is not well defined. So this is why we introduced this or minimal business, and then this O minimal business is already there. It's very popular these days, and we apply this technique to prove that this is ring homomorphism. Okay, so this is now well-defined ring homomorphism. Then now we have perfect situation to say the theorem, because we know that every compact complex manifold is definable, and we also have this well-defined ring homomorphism. So this hot theory is kind of well behaved under this thing. So we now say something like phantom and some similar to phantom and this zero divisor, blah blah blah. So we now have theorem says that. So for any some kind of actually this doesn't need to be surface, but anyway, for simplicity, let me say that I consider some base space, and I do kind of log transformation to obtain this guy. And I consider elliptic vibration, and I do log transformation. As I told you, there's no guarantee that these two are algebraic variety, but anyway, these are compact complex manifold, and this is definable. So I can say these. It makes perfect sense to measure its difference in this Grothendieck ring, and we can prove that this is a zero divisor in Grothendieck ring of definable analytic space of B. So we can say this, and indeed there are several. So from this sense, it's kind of this can be somewhat understood in a Motivic way, because the difference is now kind of Motivic invariant. And finally, let me say a few remarks. So indeed, I mean, we also proved that certain, compute some, cohomology of LVMB manifold, and a Dolbeck cohomology of LVMB manifold, and they are so-called the stabilization, process. What I mean is that if we add kind of job on this LVMB manifold, then there are certain tendency that this cohomology of LVMB manifold is stabilized. It's kind of new phenomenon. As far as I know, this is new phenomena in this non-killer manifold, and so we somewhat have some idea of how to explain this stabilization procedure in terms of this zero divisor phenomenon. So I mean, this has some. We expect this has some non-trivial consequence or some explanation. Okay, that's what I want to say.